Okay, thank you. All right, so today we're going to start a sort of a, I don't know if I call it a standalone topic, but a new topic. I'm going to start with this, with the Hamilton-Jacobi-Bellman equation. All right. Now, so thus far what we've been talking about is this construct of formulating optimality conditions, and then we have these necessary conditions, and then from that we determine extremal solutions. And then we went ahead and we talked about numerical methods where we talked about collocation, direct shooting, other techniques. Those techniques are typically what are referred to as open loop techniques. When you say open loop, it means, you have to be clear what this concept of open loop means. Open loop means that you generate the trajectory and the state and the control, and it's generated for a particular model over the entire duration of the trajectory, and there's no feedback which says that at some point I'm going to now decide what the control is based on the state of the system. That's open loop. It's based entirely on having the full problem in front of you and you're solving the full problem. So that's open loop. In this construct that I'm going to be talking about today, we're going to be dealing a little bit more with the concept of what's called closed loop. Now, Hamilton-Jacobi-Bellman equation in general problems is not that easy to implement, but it's very important from the standpoint of understanding what optimality actually means. So before I get into actually the details of the Hamilton-Jacobi-Bellman equation, I want to talk about this concept of optimality and the principle of optimality. So imagine that I have a trajectory that takes me from some point A to some point B. And I know that this trajectory is optimal. I don't care where it came from. It's optimal with respect to some problem that I've decided to solve. Now, it's really important to understand what the concept of optimality actually means once you have a solution. So if I tell you, let's take a simple case. If I tell you that going from A to B is optimal, and I'm not going to draw it on the board because I don't want to draw this on the board, but let's suppose I introduce a new point, let's call it C, which is not on this path. And I bless you, and I tell you that going from A to C, so maybe I will. So let's say I got another point out here, C, which is not on this path from A to B. And I tell you that going from A to C is optimal, and then going from C to B is optimal. Okay, so here, I'm going to draw this again. This is optimal trajectory, and I'm going to say from A to C. This is optimal trajectory from A to B, and this is the optimal trajectory from C to B. Okay? Now, if I tell you that the trajectory from A to C is optimal and the trajectory from C to B is optimal, is the trajectory from A to C to B optimal? What's the answer, yes or no? No. Can't change the problem on me. I've set up the problem exactly the way I want to. I have a point C, and I say, I go from A to C, and I find the optimal trajectory from A to C. I have the same point C, and I say I find the optimal trajectory that takes me from C to B. Now I ask you, is A to C to B an optimal trajectory? Why not? Because A to B, I told you, was optimal if I'm going from A to B, right? So the statement of the concept of, so this concept of optimality only applies if you pick the point C to be on the path from A to B, which you know to be optimal, right? Which is basically what the principle of optimality says. So you have to be very careful about the principle of optimality. The principle of optimality says the following. I mean, you can say this in a lot of different ways. But the principle of optimality states that given an optimal path from A to B, any 2 points on this path constitute our optimal with respect to start, I should say there, any 2 points on this path. Sorry, I have to write this really clearly. I should say the path taken between any 2 points on this path is itself optimal. So what it says is that if A to B is optimal, and I take a segment of A to B, and I call this point D, and I call this point E, the path from D to E, which is a subarc of the path from A to B, is itself optimal. All right? That's what it says. That's the principle of optimality. Now, before we get into this, okay, because there are 2 aspects to this. One is math, equation, and that's all fine and good. All right? Math and equations are great, but the fact is you got to understand what it is that's going on here. So you don't do this. You don't realize you do this. But let's take a situation where you actually like a practical life situation. All right. Let's suppose that you decide you want to take a road trip from New York to Los Angeles. All right. And you're not, going to drive continuously for whatever time it takes you to get there and stop for gas and not do anything else. You're going to stay overnight. You're going to like pick places to stay, and you want to get there in a certain way. Let's suppose you say you want to minimize the time it takes for you to get there, but you need to do this in such a way that you need to plan a route. How are you going to plan a route? Or let's say you want to minimize fuel. So whatever the criteria is. When you plan the route, you don't realize you plan it this way. Because if you don't plan it this way, you'll realize that in the end you'll wind up having to make all kinds of corrections. If I start off from New York and I start driving westward towards California, what's going to wind up happening is you're going to say to yourself at some point, am I on the right path to get me to Los Angeles, right? You have to know that path. So what do you have to generate when you start? You have to generate the entire trajectory that gets you from New York to Los Angeles. You have to know, I'm going to take Interstate 80, and then I'm going to switch over to the Ohio Turnpike, and then I'm going to be doing this, then I'm going to be doing this other thing, and eventually I'm going to wind up on this other road. Then I'm going to go on Route 66, and I'm going to listen to Nat King Cole and all this other stuff, and then basically you're going to wind up in Los Angeles, right? So you say to yourself, I got a path that I've constructed. So I've got the entire path that takes me through all the interstates, wherever I'm going to stop along the way for fuel and where I'm going to stay overnight. Now I have the whole path. Now what you do is you actually work your way backward from the end back to the beginning to figure out if I'm somewhere along the middle, where is it that I need to go from here to the end in order to be able to make myself optimal with respect to the rest of the path. So you're always working your way backwards. You're always starting at the end, and you're saying, okay, if I drift my way back away from Los Angeles a certain amount, now I'm here. Now what I need to do is from here, I need to determine what the optimal trajectory is that takes me back to Los Angeles. And so then you keep going backwards, and so you're basically receding this initial condition, and this initial condition keeps changing until you finally get back to the actual initial condition that you need, and then you've generated the entire path. So this is Bellman's whole real-life concept, is you live your life forward in time, but you plan it backward in time. You plan from the end back to where you are, and then you work your way forward using that plan. So you think about it on a daily basis. You do this all the time. You don't realize you're doing this. If you're a very organized person, you plan your day and you say, okay, these are the things I need to get done today. So that by the end of the day, I need to have finished all these things, right? But if you start your day off and you say, okay, I'm going to do one, then I'm going to do two, and then I'm going to do three, you have no idea whether you'll actually get done with everything that you need to get done. You first need to have generated the entire plan, and then you work your way from where you are to be able to finish whatever the remaining part of the plan is. So you're always going backward to the point you're at, and then the plan then says, all right, now I'm going to execute this plan forward. So I keep going backward to where I am, and then I execute the plan. And when you go all the way back to the beginning, you've executed a plan for the entire day such that you know that if you carry out that plan forward in time, you wind up being able to complete all of it, right? If you do it one step at a time and you say, okay, I'm going to do this, then I'm going to do that, and I'm going to do this, I'm not going to worry about whether I get done at the end, you may never finish all the things that you think you need to do. You need to first get the entire plan and then work your way through the plan. It's always a receding problem that takes you back. This is the whole concept of optimality when it comes to control, is that you're always working your way back from the end back to where you are and then working your way forward. So let's look at this in terms of optimal control. So consider again the state dynamics. So this is the problem we've been doing the whole time. X dot equals f of x of t, u of t, and t. All right, now everyone's happy because there's math, right? So when you have to actually think, nobody likes that. People like math. They can just plug into equations, right? So this is an equation, so I can write it down, right? Don't ever fool yourself, okay? This is actually just English written in symbols, all right? That's all it is. It's nothing else, right? You have to ultimately know what it is that this means, right? If I give you hieroglyphics, most of you probably have no idea what's in hieroglyphics. Right? Neither do I. I don't know hieroglyphics, right? So if I give you, camel, squiggly, or some other hieroglyphic symbols, you need somebody to translate for you in order to be able to tell you what that means, right? So the symbols mean nothing, right, until you put meaning to them, right? So this whole thing means nothing until you put a meaning to it, right? This may as well be written in hieroglyphics. It could be written in some other language that I don't know, right? Doesn't matter. The point is, if I don't know what this means, this is a meaningless statement. It has to ultimately be translated back into language, right? So now. And let's suppose you have the cost functional. And it doesn't really matter whether you put a Mayer cost on this, but we'll put a Mayer cost on it. J, which is a function of x of t0, which is equal to s. I'm only going to deal with a final state in this case, plus the integral from t0 to tf of v x of t, u of t, t. Okay. Now, that's the problem that we have, okay? I want to minimize this subject to this constraint. Now, I've got x at t0 is a fixed quantity in this case. X at t0 is equal to x0. It's a known quantity, all right? Now, suppose that instead of writing this cost functional in terms of t0, I do exactly what I just said, is that suppose we write j, not of x of t0 anymore, but of x of t. So now I got to be a little careful here because j of x of t and t is equal to the integral from t to tf. But because I've written this in terms of t, I got to change the argument in here. So x of tau, u of tau, and tau d tau. Now, what I'm going to do is I'm going to say, let's suppose that I've generated the optimal solution. So what I've done is I've said I'm generating the optimal solution. I'm generating the optimal solution from t to tf. So if I'm sitting here and I'm looking at this trajectory, right, there's t0, there's tf, and here's t. T is sitting here somewhere, right? What I've done is I've said I'm generating the optimal trajectory that takes me along this part of the trajectory, right there, right? So this is x of t, and this is the final value, right? X of tf. So what I've got here is I've got x star on of t, well, x star, which takes me from capital T to tf. I'll denote it that way, okay? So that's what this is. That's what that cost represents, right? Now, and then what have I got? I've also got plus s of x of tf and tf. And there's a star here. Okay? Now, let's suppose that I take this and I'm gonna do a couple things to it. So the first thing I'm gonna do is I want to take dj dt, where this is evaluated at x star of t, okay? So I'm going to take this derivative. So what is this derivative equal to? Well, this derivative is equal to the partial of j with respect to, bless you, x star of t times what? Times x dot star of t, right? Plus the partial of j with respect to t. I haven't done anything. I've just taken the total derivative, right? So this is there's nothing in here that's mysterious. The derivative here is a function of two things, right? It's a function of the derivative of, because there's a t in here and then there's a t in there, right? So I've got two parts to this derivative, right? So, but we know that if I take the derivative with respect to t, what do I get? If I take this thing, you see that there's an integral in here, right? So you know that dj dt, where this is evaluated, be really careful, x star of t and t dt is equal to minus v of x star of t u star of t and t. And that just comes from the fact that if you just take the derivative here, you're taking the derivative of this integral, which gives you back that. Okay? So there's nothing fancy in all this. Now, so now if I take this and I substitute all this in, what do you get? So therefore, if I just do the substitution, what do I get? I get minus v of x star of t u star of t and t is equal to what? It's the partial of j with respect to x star of t times x dot star of t, and then I get plus the partial of j with respect to t. So let's be careful here. There's so many stars. A lot of stars. Okay, so now if I look at this and I say, all right, well, what's x dot star of t? But x dot star of t is equal to f, right? Because that's my dynamic. So I've got x star of t, u star of t, is equal to the partial of j star with respect to x star of t times f of x star of t, u star of t, and t, and then I've got plus the partial of j star with respect to t. So suppose that we put everything on one side of the equation. So if I rearrange this, what do we get? We get the partial of j. Now I'm going to be a little bit more explicit. X star of t and t with respect to t, plus v of x star of t, u star of t, and t, plus the partial of j of x star of t and t with respect to x star of t times f of x star of t, u star of t, and t is equal to 0, right? Oh, I got to be technical. Okay, all right. So suppose now we define. If you look at this equation, you'll say, "Well, that just looks crazy." Well, here. Suppose now that we define the Hamiltonian. The Hamiltonian is h. And if you look at the structure of this, what is the Hamiltonian in the case of a regular optimal control problem? It's the Lagrange cost plus lambda transpose times the right-hand side of the dynamic. So if you look at this, I've got almost the exact same thing. I've got v of x of t, u of t, and t, plus the partial of j with respect to x transpose times f, right? So x of t, u of t, and t. So if I write this in terms of the Hamiltonian, then what you get is that the partial of j star of x star of t and t with respect to t plus h of x star of t, the partial of j star of x star of t and t with respect to x star of t, and t is equal to 0. With the boundary condition that j star of x star of tf and tf is equal to s of x star of tf and tf. Now what have I done? So this looks kind of crazy because you say to yourself, well, that doesn't look very appealing, right? But the truth of the matter is, when you look at this, look what it generates for you. It's very hard to see this because there's a lot of math in here, right? But what it says is that if I'm going to figure out the optimal trajectory, what it says is if I integrate backward from TF back to T, right? This is what this integral is doing, right? It's starting at TF, and I'm integrating back to a point here, T, right? You see that in the integral? You see that I'm starting at TF, and I'm integrating back to a time T, right? I'm going from here to there. I'm not going from T0 to here, right? This is what's happening, right? I'm taking this problem, and I'm making it into a problem that goes from the end back to where I am, right? If little t is the current value of time, it says get me all the cost that has accumulated, or the value that's accumulated from the endpoint back to where I am. It's not the cost that's accumulated forward from the beginning to where I am, right? So I'm not accumulating cost from the beginning to where I am. I'm figuring out how much cost there is left to go, right? Because when I'm all done, I will have utilized all the cost. It will have been done, right? It will have consumed all the cost. There will be no more cost left to go. So this problem becomes a backward time problem that says figure out for me from where I am to where I'm going, what's the optimal amount of cost left to go, right? That's what it's telling me. That's what this equation is telling me. So this equation is absolutely the reverse of what it is that you intuitively would think. You would intuitively think, well, I got to go forward, right? That's a different question. Now it's when I execute the plan, I'm going to go forward. But when I'm figuring out the plan, I'm starting at the end and working my way back to where I am at the beginning. So now let's take this all the way to its limit. When I'm at T0, I figure out the entire plan. I say the amount of cost that's left to go is everything, right? Because I haven't accumulated any costs because I'm starting at the beginning, right? Now I move along the optimal path a little ways. And I say to myself, okay, now let's suppose I'm here. If I'm here, and this is some other time that's between T0 and TF, now I got to ask myself the question, from here to the end, what's the optimal solution? The optimal solution is to give me the path that generates the optimal amount of cost to get me from where I am to the end. Think about this as you actually do it in real life. This is how you actually do it, okay? In real life, all of you have some familiarity with this, so I'll talk about it in more general terms. In real life, nobody ever is able to do anything perfectly, right? We have errors, right? Models have errors. There's noise in measurements. There's all kinds of things that happen in control systems, right? So if I generate a path based on a particular model, I have a model for my dynamic system, right? Here's a good example, all right? What would you do if I told you that you need to go from here to the mall? Tell me a quote optimal route to get you from here to the mall. Let's say it's just a route that you would normally take. Well, you get off campus, you get on university turns into Newbury, and you follow Newbury all the way to the mall, right? But now let's suppose that I'm driving on Newbury Road, or I'm driving on University Avenue, and I hit the 34th Street intersection, maybe the 43rd Street intersection. Okay, let's go a little further. 43rd Street intersection. And then there's a detour. Let's suppose Newbury Road was closed for 2 blocks after 43rd Street, right? Now, what would you have to do? Suppose it was closed, but you still want to go to the mall. Now, what would you do? The road closed, okay? What would you do? Take a different route, right? But how do you figure out that different route? Now that different route, assuming that road is closed and you can't go that way, you have to replan, right? You've got to do the plan from where? Not from back at the beginning. You've already taken that amount of time to get you to where you are now. You're not going to go back to the beginning and say, well, I'm going to go back to the University of Florida and start all over again, right? You're not going to do that. You're going to say, from where I am, what is the best route that I can take to get me to where I want to go, which is the mall, right? So your replan always takes place based on wherever you currently are. That's exactly what this equation tells you. This equation tells you that from where I am to the end, I need to figure out how much cost there is left to go in the problem, right? Because that optimal cost, that's the path I want to take. I want to take the one that has the least amount of cost from where I am to the end. It just so happens that in this particular case, I haven't deviated from the original path. So if suddenly the road said, you're driving on Newbury Road, and you see 2 blocks ahead that it says the road is closed, but as soon as you get there, they lift the detour, and they say, oh, road's open now, right? You just keep right on going on the same path that you were going to go on before, right? Because it was closed before you got there, but now it's open again, so you're going to keep going, right? You're not going to change your plan, right? The thing is, you've already calculated the plan. If you stay on the plan, then there's no problem. You know every single one of these points. You know all these values of x, and you can always tell yourself what the path is, right? The point is that at any point in time, if I don't know what the plan is going to be the one that minimizes whatever the cost is that's left to go in the problem, which is what that is. This equation right here is what's called the Hamilton-Jacobi-Bellman equation. Like a lot of other things in life, we really should have a course in advanced dynamics in the MAE department at the University of Florida, one that goes beyond 5215, because one of the things that you learn in that class is you learn the structure of dynamical systems that are governed by Newtonian mechanics. And one of the beautiful things that comes out of this is this thing called Hamilton-Jacobi theory. Hamilton-Jacobi theory is exactly this problem. It tells you how you actually figure out what the paths are that you would take along a trajectory to get from the path that you should take in order to be able to minimize what's called an action integral. This all comes back to action integrals. Laws of nature minimize action integrals. This is Hamilton's principle. It's the whole concept that drives Newtonian mechanics. And the equation that governs this is what's called the Hamilton-Jacobi equation. Well, the Hamilton-Jacobi equation, if I drop Bellman for a minute, all right, let's just drop Bellman, all right? Hamilton-Jacobi equation is this equation for a mechanical system, governed by Newtonian mechanics. But it turns out that in optimal control, you get this exact same structure. When you actually look at this problem as being a problem that recedes the initial condition back to the beginning, the problem from where you are to the end with the cost to go gives you the exact same equation. Isn't that weird? Do you find that weird? You should find that really weird. Optimal control has nothing to do with Newtonian mechanics, right? Absolutely nothing. They're completely different subjects. One's a mathematical subject. One tells you how physics actually works, right? They have nothing to do with each other. They satisfy the exact same equation. So this guy Bellman came along in the 20th century, and he said, I'm going to do this whole thing, this construct, which by the way is called dynamic programming. This is continuous time dynamic programming. Most of the time people describe this as discrete dynamic programming, and I'll talk about discrete dynamic programming later. But the equation that he came up with was this thing. He said, well, I got this equation. Now, of course, Bellman was a really smart guy, and Bellman did a lot of wonderful things, but Bellman wasn't full of himself. So he didn't name it after himself. He didn't say, I'm going to call it the Bellman equation. He just said, this is the equation that I get. Somebody else named it the Bellman equation. And then they figured out that, it's the same equation that Hamilton and Jacobi came up with, so they call it the Hamilton-Jacobi-Bellman equation, right? By the way, if you want to know who Bellman was, Richard Bellman I don't know when he died. I think he died in the 1980s. And he was a professor at the University of Southern California. He also worked at the Rand Corporation in Santa Monica, which is also in California, right down the street from USC. And he sort of invented this whole concept of dynamic programming. This is Bellman's contribution to the world. Richard Bellman was a really famous guy. I mean, like, if you want to go back to the original work in optimization theory, dynamic optimization, all of the great work was done by Bellman. I mean, Bellman was like, larger than life, and he left behind this absolutely masterful theory that describes this construct that life has to be planned backward in time. And he always used to say that life needs to be planned backward in time. It makes no sense. You say, well, how can I plan for something that hasn't happened? Well, that's the whole point, is that because you don't know what it is that's going to happen, you plan the best you can based on what you think is going to happen, right? Isn't that what you do? You always do that, right? You plan things based on what you think is going to happen. If you're driving from here to Orlando, you say, well, I'm going to go down Interstate 75, and then I'm going to go take the turnpike, because that's what you think is going to happen. But if I'm driving along and all of a sudden Interstate 75 or the turnpike is closed, you say, well, what I thought was going to happen isn't happening anymore, so I got to figure out another way to do this, right? That's exactly what you do. Then you replan. And then you replan again if you need to. And you keep replanning until you finally get to whatever it is that your goal is, right? And you do this every day when you study, when you work. You say, oh, I'm going to spend the next 4 hours studying such and such course. And you say, this is what I expect to get done by the end of the day. But the reality is you almost never get that done. Why? Because along the way, you realize that there's something else that you didn't think you needed to know that you now need to know. So you go study that thing for a little while, and then you have to replan how you're going to get your understanding of the subject done so you can finish your homework assignment for the class, right? It's not a straight line. You don't always get things exactly the way you want. Now, this can be expanded upon even more, because if you look at this, there's actually more structure to this than meets the eye. So now what we do is we take the next step. It's a pretty cool subject, actually, dynamic programming. It's got all kinds of computational issues associated with it, but from other perspectives, it's a neat subject. So suppose we do this. So from the definition of the Hamiltonian, so if I go back over to that definition of the Hamiltonian in here, if I was doing this with calculus of variations, what would this Hamiltonian look like? Come on. We're like 10 weeks into this class now. What would this Hamiltonian look like if I was doing this with calculus of variations? Lambda transpose F. So what inference can I make from that Hamiltonian?
dj over dx is the lambda from before?
Right. The lambda star is equal to the partial of j of x star of t and t dx star of t. Right? Makes sense? I mean, it's consistent with that definition and the one we used earlier, right? So, also, what else do we know? We know that lambda dot star of t, having nothing to do with this, what's it equal to? Come on. You're 10 weeks into an optimal control class. I've gone through this many times. What's lambda dot equal to? Minus the partial of h with respect to x star of t transpose, right? Actually, this is a transpose. Okay, so what can you tell me from that? I got two things on the board. Forget about the rest of the board. Look at these two things, all right? Don't tell me about what you learned in 3rd grade. Don't tell me about the science project you did in 8th grade. I want you to stare at what's on the board and tell me something. What can I do? Yeah, differentiate the first one, right? So lambda dot star of t, okay, is equal to what? It's equal to d dt of the partial of j of x star of t and t with respect to x star of t transpose, right? there a transpose in there? Let me make sure that I do this right. No, this is just, there's no transpose. Okay. So what does that tell me? What's that equal to? What's this equal to? It's got to equal that, right? Okay. Now, suppose we make the following substitutions. They're not really substitutions, they're shorthand. Then we get J star T plus H of X star of T, J X star, U star of T, T equals 0. Yeah. So let's make sure I didn't forget a. Darn. Okay. So, now let's look at this. You can see that this equation, it's the same equation that I had up there before, but I just wrote it in shorthand terms, which is that you can see that what it does is it gives you a way of generating essentially a feedback law. Because what you can do is, if you take that path that takes you from T to TF, at every point along the trajectory, you can ask yourself the question, what is the optimal path from where I am to the end? The optimal path from where I am to the end has to satisfy this equation. This equation has in it the control. So as a result, if I can solve this equation, at each step, I can get the control. So this is very abstract. So what I'm going to do now, and this is what we're going to finish this lecture with. I hope I can get it done. We'll try it anyway. Let's do an example. Suppose I have the following problem. J is equal to 1/2 x squared at TF plus the integral from 0 to TF of x squared of t plus u squared of t. And my dynamics are x dot of t is equal to minus 2 x of t plus u of t. And I've got the initial condition x at 0 is equal to x0. Let's do this using, or at least we'll start doing this with Hamilton-Jacobi-Bellman equation. So let's identify all the terms in the equation first. All right? Just first, I've got v of x of t and u of t is equal to 1/2 x squared of t plus 1/2 u squared of t. That's what's inside the integral. All right? I've got my Mayer cost is equal to 1/2 x squared TF. And I've got f of x of t, u of t, t is equal to minus 2 x of t plus u of t. All right? Now, let's figure out everything. So, what is my optimal Hamiltonian? This is going to equal 1/2 x squared of t plus 1/2 u squared of t. That's my Lagrangian. Plus jx star. These are all stars. Times minus 2 x star of t plus u star of t. All right. Now, because the optimal control is obtained from dh du equals 0, what that tells me is, it tells me that u of t plus jx has to equal 0, which tells me u star of t has to equal minus jx star. That just comes straight from taking that Hamiltonian and just differentiating it. So, and as a result, the h is going to equal 1/2 minus jx squared plus 1/2 x squared of t, and then plus jx times minus 2 x of t minus j of x, which is equal to minus 1/2 jx squared plus 1/2 x squared of t minus 2 x of t j sub x. So the Hamilton-Jacobi-Bellman equation is jt plus h, which is equal to jt minus 1/2 jx squared plus 1/2 x squared of t minus 2x of t jx is equal to 0. And the boundary condition, which is the cost at the end, okay. I don't have enough time to do this. Maybe I do. 3 minutes. I do. Okay. All right. Now, we know that. Oh. So let's look at this. Okay. So I've got this equation down here. So if you look at this, you'll see that this is a partial differential equation, right? It's a partial differential equation in t and in x. And in this particular case, you can actually make a simple substitution to assume a solution just because the system happens to be linear with a quadratic cost. So assume the solution has the form, which is j of x of t, and t is equal to 1/2 p of t times x squared of t. So if you do that, you can see that j of x of tf and tf is equal to 1/2 p of tf times x squared of tf, but that has to equal the boundary condition that's up here, which is 1/2 x squared of tf, which tells me that p at tf has to equal 1. And also, if you take the derivatives here, you'll see that jx, which is the partial with respect to x, if I take the derivative with respect to x, what do I get? I get p of t times x of t. If I take the derivative, the partial derivative with respect to time, now if you look at this, you'll see that if you take the partial derivative with respect to time, this is not part of the partial derivative because p is the only thing that is an explicit function of time. This is the thing I'm solving for, so this is not the thing I'm taking the derivative with respect to. So what you get is you get 1/2 p dot t times x squared of t. Now, if you substitute all those things in, you get that the optimal control is equal to minus p of t times the optimal state. So now you can see that if you put this in, because if I'm almost done here. We'll do the rest of it on Wednesday because it's not the important part's over. You'll see that the optimal control here is minus jx star. So jx is p of t times x of t. So the optimal control, you can see, is now a feedback law. You see that? That at every step in time, I determine the control from the value of the state, right? The optimal control is some function of time times the optimal state. So here's my feedback law. So you can now see that using the Hamilton-Jacobi-Bellman equation to solve this problem generates this feedback law for me. So I'm going to finish this example next class, and then we're going to go through the more general linear quadratic problem, which actually I'll show you how to actually solve that one more generally for the feedback law, and then we'll have another way of being able to do that same problem that we did earlier in the semester. Okay, so this is just the starting point.